Okay, good afternoon. Sorry I couldn't be there on your first day of in-person, so we have to do this over a YouTube video, I guess. But hopefully we still get this stuff done here. So to start off with here, I have 3 pictures. I know you're not able to be in groups this year, but we're going to start off with about 30 seconds maybe. I want you to just pause the video and think about what kinds of symmetry you see in each of these pictures. Remember, we talked about 2 different kinds of symmetry. That was reflective symmetry, where something looks like it's a mirror image of itself. And then we've got rotational symmetry, where something looks like you can turn it a certain number of degrees or a certain part of a circle, and it would look the same as it does now. So maybe pause the video here, think about that for a little bit, maybe talk about that with someone nearby, and then start the video again. Okay, so there's a lot of different types of symmetry on here. A lot of people start with the flag. The flag has reflective symmetry. So if I were to take a line, we call this the line of symmetry, right down the middle, if I folded that flag over, it would match up exactly that way. And I could also fold it like this, top to bottom, and it would match up that way. Now, one thing a few people always ask about is, could I fold it like this? And it kind of looks like it should work, but because this is a rectangle, it ends up not quite working out. If it was a square, it absolutely would, but with the rectangle, it doesn't quite. Now, another thing that you can do with this is it actually has rotational symmetry. So if I take this thing and I just turn it 180 degrees, it looks exactly the same as it used to. And so we call this twofold rotational symmetry. Now we've got these other examples here that might be close to having reflectional symmetry, but there's a little details in there that make it so they don't. If you were to draw a line right down the middle of this, it looks pretty close, but you'll notice there's arrows on one side and not on the other. So that one doesn't quite work. What this one has is that threefold rotational symmetry. Oops. Apparently my pen decided to stop working there. Threefold rotational. So what you can do there is you can take that shape and you can fold it like rotate it a third of the way, and another third of the way, and another third of the way. It looks the same. And this last one here is sixfold. So if I turn it like that, once, twice, 3 times, 4 times, 5 times, and 6 times, I'm back where I started. So that one is sixfold rotational symmetry. So that's just a little review of some stuff we talked about way at the beginning of the year, but is very much related to what we're doing right now. So today we're going to start our conversation here on transformations. A transformation is just taking a picture or a shape or something and doing something to it to make it different. So the ones we're going to talk about are rotations, reflections, and translations. There are other ones that we'll talk about later on, but those are the 3 that we're going to hit today. Of these vocabulary words, probably the biggest one is going to be the word image, and then the 3 transformations. Line of reflection, translation vector, those aren't too super critical. These are all called transformations. And we will talk about the difference between a rigid and a non-rigid, but the ones I circled are definitely the most important here. So our first thing here is we've got a little picture of all 3 transformations. And in geometry, we call these things rigid transformations. And it's really important why we call them that. When we think about the word rigid, the idea is that shape is not changing, that it's not being smushed or stretched or shrunk or anything like that, that these shapes are exactly the same as they were before, just moved in some way along the paper. So with a translation, you've probably heard called a slide transformation before, but the mathematical term is translation. A rotation is kind of just like a turn. You're taking that whole thing and rotating it. And then a reflection, you want to imagine yourself like a mirror. You're taking something and reflecting it or mirroring it across a line. Like you imagine looking in a mirror here, and that's what you'd see over there. 2 keywords you see on this page are going to be original and image. The original is kind of self-explanatory. That's what we call the shape or the figure before it's been changed at all. The image is what we call the after, right? After you've done this transformation, then we call it the image. Sometimes you'll hear the word pre-image for original, but your book uses original instead, which I think makes a whole lot more sense anyway. So pause the video, and you've got a big challenge here. I want you to try to read that. Go for it. Okay, and be honest here. Anybody succeed? I think in the A groups we had last week, I think someone made it about halfway through before they gave up here. I'm going to try it though. I've read this thing for like 4 years, so I pretty much know what it says anyway. So it says reflection is a type of transformation that produces a figure's mirror image. If you draw a figure onto a piece of paper, place the edge of a mirror perpendicular to your paper, and look at the figure in the mirror, you will see a reflected image of the figure. The line where the mirror is placed is called the line of reflection. So if you can imagine doing that, that's one example of where you've seen a reflection before. Another example of where you've seen a reflection before, and I know you can't see that, is something like Snapchat or Instagram. So when you normally take a picture with your camera, or if you've used your webcam and you've had like writing on your shirt, you'll notice the writing on your shirt looks like this in the picture here. If you've ever taken a selfie on Snapchat, though, you'll notice that the writing looks correct. You can read it on Snapchat. Snapchat actually takes that picture from your camera, which is a mirror image of you, and actually flips it back around so that you can read things like words, and it looks more appropriate on the picture. So that's one thing you've seen before with reflections. Hi. We've got another example of the original here and the image here. Notice the line of reflection being put there. And then the same thing here, the original in black and then the image in blue, just a mirror image. That line can go anywhere you want. Okay, next up, normally we do this little activity in class with the patty paper. We're going to skip over that. We've got an online version we can do too of examples of reflections. So we've got one here. I've called it the dancing man. We should probably change that to dancing person. But I've got a reflection here of a person, right? The one on the left is the original, and the one on the right is the image. I don't think I can I can't move that one, but I can move this one. And you'll see when I move the person on the left, the person on the right moves as well. Now, a couple of really important things I want you to notice. If I make the arm longer, you'll notice the arm in the image, the one on the right, gets longer as well. If I change the angle between his legs, you'll notice the angle between his legs changes on the image, the one on the right, as well. In general, this person here and this person here are the exact same person. They are identical to each other, or in geometry terms, they're congruent. But there are some differences. Just because they're congruent doesn't mean there aren't differences. When I was moving the left hand of the person, which hand moved in the image? Well, it's the right hand. If I moved the right foot in the original, then the left foot moved in the image. And that's going to be true no matter how I draw my line of symmetry. Even if I put the line of symmetry like this, and maybe I want to put it like way over here and reflect them the other way, it still happens. If I move the left hand on this one, the right hand moves on the image. So we've got that kind of backwards thing going on there. Then we've got this one. Let's see if this one works. There we go. So now we've got it with some actual geometry terms here. Uh-oh, what's going on there? Okay, I think we're okay. Some actual geometry shapes. This is a quadrilateral, A, B, C, D. Now, a couple of things you'll notice. These two shapes are exactly congruent. The line segments are all the same. The angles are all the same. These shapes are congruent. But what you're going to notice here is the order of the letters has changed. Here it goes A, then B, then C, then D, going around in a clockwise motion. Or sorry, that's counterclockwise. On the other side here, A, then B, then C, then D goes around in a clockwise motion. So this one goes this way, this one goes this way. All right, so a couple of interesting things there with reflections. So we've got a couple of questions here that I usually have you answer. These might be a good one to take a look at those questions, pause real quick, and and reflect on those and see if you think about the answer there. Okay, so a couple of these questions, those first three we really talked about already. If we reflect anything over a line, it's definitely going to be congruent to what was there originally. We saw that with the person, the arm stayed the same, the angle stayed the same, those quadrilaterals stayed the same. They are congruent to each other. Number 4, if a set of points are collinear, will a reflected image be collinear? We can actually try that again right on here. If I were to put like point C right on that line, I could even do all 4 points right on the line, right? They're all on that line there. In the image, they're all on that line there. It's a different line, but they're all 4 collinear, all 4 collinear. And then number 5, is the segment that connects each point to its reflected image always perpendicular? Let's take a look at what that looks like. I'll go ahead and make that in this figure. So if I were to grab a segment tool and connect A to A prime, what I'm looking for here is right at this place where they meet. You notice how that's a nice 90-degree angle? Do you think that's always true? Let's try another one out. If I go from B to B prime, looks pretty 90 degrees, doesn't it? So again, that one is always true as well. Okay, moving on to rotations. This one's a little easier to read, so pause the video and go ahead and try that one out. So this one says, again, I'll read it if you're having trouble with this. It says a rotation is another type of transformation. In a rotation, all the points in the original figure rotate or turn an identical number of degrees about a fixed center point. You can define a rotation by its center point, the number of degrees it's turned, and whether it's turned clockwise or counterclockwise. If no direction is given, assume the direction of rotation is counterclockwise. And so the really important things here, you've got your center of rotation. That's the point that's kind of being held still. All the other points are turning a set number of degrees around that. And what that means is the angle that they form. So if I'm looking at this point here, that looks just about like 90 degrees, right? If I'm looking at this point here, just about 90 degrees. So every single point there traveled 90 degrees clockwise. Okay, so we could do this on patty paper again if we were in class. We'd start by just tracing our figure. We'd hold our pencil right on that point and we just turn that top piece of paper, and that would be our rotation. Well, we can do this in online too here. So let's take a look. This first one I think is the dancing person again. Okay, there I've got my dancing person. And you can see what happens as I rotate. I increase that angle. You can see the angle down there in green. There's 90 degrees. There's 180 degrees. There's all the way around to 270 and 360, right back where we started. Now, a couple of things here that are different than a reflection. With the rotation, you notice with the reflection, when I moved the left hand, the right hand in the image moved. Here, when I move the left hand still moves. So that kind of thing where it's mirrored is gone now. This is just turning. There's no mirroring going on at all. The next thing I want you to notice is they're still congruent to each other. If I make the arm shorter in the original, the arm gets shorter in the new one. Make it longer, it gets longer. Change the angles change in the other one. These always stay congruent to each other. The one big difference here is, do all the points move the same distance? And the answer here is no. The points closer to the rotation point, that center of rotation, don't have to move as far because they are closer. In this case, it'd be like if you've ever seen a marching band go around a corner, you know the inside people have to go a lot slower than the outside people. They end up taking really small steps, where the outside people take really, really big steps. Or if you've ever seen somebody run track, or if you run track, they stagger the starts because the inside track is actually shorter than the outside track. So if they all started at the same point, the inside people would have a lot shorter distance. They can't do that. Okay, and then we want to take a look at a quadrilateral here too. So for a quadrilateral, we've got the same thing going on. You'll notice that the points closer to the circle are moving less, but other than that, all the angles, all the sides, everything about these shapes stays the same. They are congruent to each other. So we can talk about these questions. They're pretty much the same ones. Number 1, what stayed the same? All the segments, all the angles, all the polygons stayed the same. The one different question here is something like number 6. Are all the original points and their image points the same distance from each other? And that's the one we said is no, that the points further from that center point have to move further. I guess one question we should talk about here is number 5. If we take a polygon ABCD and rotate it, it's going to be now called A prime, B prime, C prime, D prime. The only difference is we add those prime symbols in there. Every time we make an image of a shape, we add the prime symbols to the new ones. And you can actually see that happening here. We've got these little prime symbols there. I've got the prime symbols there. That's just how we show which one's the original, normal letters, and which one's the image, which is the prime letters. Okay, our last one is a translation. I think all of you can read that one, no problem. So translation is the simplest form of transformation. You can model it by tracing a figure onto patty paper and sliding it along a straight path with no turning. You've called this a slide transformation before. They want you to notice that all of the points travel the same distance and along a parallel path. And that distance they travel is called the distance of translation. Because it's all going in a particular direction, we can call this a translation vector. And if any of you have seen the movie Despicable Me, you know a vector is just a mathematical quantity that is made up of a direction and a magnitude. Distance is a type of magnitude. And we represent it with an arrow in mathematics. So you'll see that on the next slide here. So here we've got a couple of examples of translations. Here we've got a seashell that has been translated to the right. This is the translation vector right there. If you'll notice that, let's see, can I just grab that? No, I cannot. If I take that translation vector and I just trace it here real quick, every single point moves that distance. If I look at the top of that seashell, that's how far it moves. If I look at this little point here, that's how far it moves. If I look at this corner, that's how far it moves. Every single point moves that exact same distance in that exact same direction. And the same thing happening here on patty paper. The distance from that point to that point representing your vector. Now, translations are also the easiest ones to do on coordinate grids too. They still have that translation vector. And so if you're thinking about this, the black one there is the original and the red one is the image. The translation vector would be represented by an arrow like that. And what you're going to notice here, that vector is the exact same for every single point. Now, on graph paper like this, we've actually got it a little bit easier. If we wanted to, we could think of this as 2 translations happening at once, and they'd be a lot easier to think about. We could think of it as translating 5 units over to the right-hand side, and then translating 3 units up. And that lets us go and just count the boxes rather than having to figure out how long this vector is. And that's actually what we're going to do tomorrow when we start talking about how to translate these shapes on graph paper. So we can probably skip the dancing person here. Let's just go straight to the quadrilateral. I'm going to blow this up a little bit. So here we've got our translation vector. So I can make it as short, if I get basically down to 0, it doesn't move, or as long as I want. I can make it go right off the screen. The main thing here is, in this case, nothing is twisting, nothing is turning. All the line segments you'll see are staying the same, just like you'd expect. All the angles are staying the same. These are congruent shapes. So we've got some questions there. Again, kind of the same basic ones here. If you translate anything by a vector, a segment, an angle, a whole polygon, it's always going to be congruent to the original. It's still going to be called the same thing here. It's going to be called A prime, B prime, C prime, D prime. Just adding the primes in there. Are all the points and their image points the same distance from each other? Absolutely. This is the only one where that's the case. They all travel that exact same distance represented by the vector. Okay, so here's where we got a few things. You got kind of an option of what you're going to do today. I'm just stopping here today because tomorrow we'll actually talk about how to do these, and I don't want to jump into that today. if you've got some extra time left over here, what I want you doing with the rest of your time is looking back at what you were supposed to have done Monday and Tuesday. I'm going to guess there's quite a few of you that did not get all of that done. For this one here, this vocab review, when you click on that, it's going to be like a PDF that you can open up. You can print this off if you want to. You can also just make a copy of it on paper. What you're doing here is just filling in the missing boxes. So they give you one example, but I'm going to go ahead and talk about another one. So if we see the sentence in English, Ray CD, what I want you to know here is that is, whoa, that's not it. That's an R. It's going to be CD with the little Ray symbol over it. And if I were going to draw that on paper, I'd have C, D, and the Ray. And I want you just to do that same thing for all the other ones. You've either got a picture, or I want you to turn it back into the geometry notation or the English sentence, or you've got something like a description that I want you to draw a picture of, or anything like that. For now, you're going to have to stop at the end of the second page because those transformations we haven't talked about yet. If you'd like to give them a try, certainly go for it. But I bet you could probably do number 3. But we will talk more about how to do those on graph paper later on. Let me go ahead and get rid of those. You've also got the chapter review assignment here. Oops, that's not it. That was the Tuesday activity. Again, most of that you can do. If it gets to something about transformations, then you can go ahead and skip that for now. But I'm going to guess most of the transformation stuff on here you could do after today. So there's the problems that you needed to do. You've got some drawing here. You got some matching here. Make sure you're only doing the ones that I asked you to do because we did skip over some sections. There's some things in there that you probably don't know. Some more drawing. And then you've got some translations and transformations down here that I want you to try to do. These you could definitely do. Here you're just copying this figure and then trying to reflect it over. Just doing your best there to make it look like a reflection or a translation or a rotation. That's what you're trying to do there. Hopefully I'll see you tomorrow. If you've got questions, you can go ahead and send me an email real quick if you need to. I'll hopefully be able to answer those today. Hopefully I'll see you soon.